Hello everyone, good morning, good afternoon, good evening. Depends on when you're watching this lecture. This is lecture 7, final one for the semester, and in this lecture we are going to be talking about sorting algorithms, dynamic programming, and memory management. Sorting, I think these sorting algorithm and dynamic programming, when I was preparing these, so initially I was like, okay, is this gonna be a lot of material? I gotta divide this up, but sorting algorithm, they are intuitive, and so is dynamic programming. I mean, it's not a new, the concept is new. How you applied, where you applied, that's going to be intuitive to you. And then the sorting one, you will feel comfortable with it quicker. You come across some of these topics from the text, and I sit there. I'm like, okay, this is going to be really confusing. Let's figure out some easy examples. But for these, I think sorting and dynamic programming, conceptually, I'm going to talk about them, uh, and you will be able to get it. Okay, without further ado, let's jump into it. Merge sort and quick sort. That's the next one. Uh, now, how do I say this? Okay, I was trying to think of, from the name perspective, how can I make this easy for you? So if you think of the word merge sort, you are doing some sort of sorting and then you're merging, right? Um, Merging and then sorting. So it's one of those popular sorting algorithm that's based on the principle of divide and conquer. The English used this back when, if you heard the saying, the sun never sets on Great Britain, right? So they would divide up lands and then conquer them. But it's the easy concept, right? You divide up the problem into smaller chunks and then you tackle it. So when you've divided up the large problem into smaller ones, each one of the smaller problem is solved individually, and then finally you combine the solution together. Now this is we'll come back to this diagram, but this is a diagram that shows you how the merge sort works, right? So you start off with the array of numbers 6 5 or whatever container you're using, 6 5 12 10 9 and 1, and then you divide it up into two chunks and then you repeat the process up until the very end. But before we talk about that, let me talk a little bit more about this divide and conquer strategy. um, when the solution to each sub problem is ready, so first you have divided up the problem into smaller chunks, and you deal with each problem individually. And you have to know when that individual problem is solved. Okay? Um, Not just one individual problem has to be solved. All of the pieces, all of the individual pieces um, should have been solved or resolved. And then you combine them at the very end. Let's say, for example, you have to sort an array A. Okay, a subproblem would be to sort subsection of this array starting at an index P and ending at R. So you would divide first. First is division. How do you divide? You divide the start at the end. So you split it right in between. All right, so if Q is the halfway point of P and R, then we split uh, P and R, right, into two arrays, P and Q, and then Q plus 1 at R, right, because that's the halfway point. And then we try to sort both the subarrays, so you've got two subarrays um, in this problem, from P to Q and then Q1 to R. If we haven't yet reached the base case, we again divide. So you keep dividing up until you get to the base case. When the conquer step reaches the base step and we get two sorted subarrays, we combine the results by creating a sorted array from the two subsorted arrays, from the two sorted subarrays. Okay? Now this is what the algorithm is going to look like. If P is greater than R, right? So you've gone beyond, so you've pretty much are done with, then you return. That ends up being your case, base case. So recursion. First and foremost, identify your base case first. And then you do P plus R divided by 2, right? So you want to divide it in half. And then you merge sort, give it the initial array A, and then P and Q. And then you call merge sort again on Q plus 1 and R, right? So the two subarrays that you did, you call on that. And then finally you call merge on A, P, Q, and R. So this final merging is going to happen up at the very end. So at some point you're going to reach the base case, and then you start combining. To sort an entire array, you're going to call merge sort on A. The starting point is 0, and then length of A minus 1, right? You don't want to go beyond the last element, you want up until the last element. So hopefully that is, well, let's go back to this. So the algorithm that I just described there, you're going to apply it on this example and then see what you get. So you've got an array to begin with, right? And you divide it up into half, 6, 5, and 12, and then 10, 9, and 1. Well, 6, 5, and 12 gets divided up even further. So on one side you've got 6, on the other side you get 5 and 12. And then you divide those up into further, 5 and then 12. Okay, so now you're going to reach your base case. So you've got 5 and 12, okay? So you're going to arrange 5 and 12, you're going to make them one array, and then you're going to make 6 one array. But you're going to compare, 6, 5, and 12. And then what you're going to end up with is this 5, 6, and 12. So this ends up being 5, 6, and 12. And then 10, 9, and 1 keeps getting subdivided. Once you reach this base case right here, 10, 1 element, there's no further subdivision. So 9 and 1, right? So you compare 9 and 1, and then you swap the 2. Right, and then you compare again, and then finally you have this. And once you have these two arrays, then you gotta compare again, and then you end up with this final result. Looks straightforward. It's slightly confusing, but not that confusing. So try out a few examples. So look at that algorithm that I've given you. Write a few examples. Go through it. Don't start coding right away. Like I said, go through a few examples, and then after that, you're gonna jump into it. Then next up is merge sort. No, sorry, quick sort. Merge is something we talked about. Quick, it's quick. It's quick and easy. Quick and dirty. Think of it this way. It's quick, but it takes a lot of work. Now that's also a divide and conquer based approach. So in this approach, you have an array that's divided up into subarrays again. So you select one element, pivot element you call it. It doesn't have to be right in the middle, but you use an element and then you divide the rest of the array up into pieces. When dividing the array, the pivot element should be positioned in such a way that the elements less than the pivot are kept on the left side, and the elements greater than the pivot are on the right side. So you use a pivot element as your base. The left and the right subarrays are divided using the same approach. So you keep dividing it up, until you get one single element. And then, and at that point, what's going to happen is for each array, you found a pivot, and then you've arranged the numbers less on the left, more on the right. So when you've got one element, you'll probably have one element on the left of it, and then one element on the right of it. So your base case, once you reach that, then you start combining things together. Now let's look at the algorithm. First and foremost, select the pivot element. In this example, I am going to be selecting the very last element, which is 2. Okay, it's a fairly small number, but it's all the way at the end. So we call that the pivot element. And then you rearrange the array. Now the elements of the array are rearranged that the elements less than 2 are on one side, more than 2 on the other side, more than 2 on the right, less than 2 are on the left. Well, but hold on. How does this arrangement happen? Okay. You know, when I show you these steps, the thing that I don't want you to do is memorize these steps, okay? Try to understand them. If you really have to memorize them and work through the example, do that. But eventually, whatever path you take, whichever way you go, you really want to get to a point where you are, um, where you have this this algorithm understood. A, so a pointer is fixed at the pivot element. So you've got a pointer to pivot element, and it's compared to the elements from the beginning. So you start off, you got one pivot element, and that's compared with elements from the beginning. If the element is greater than the pivot one, then the second pointer is set. Okay. The first comparison that you did, if you found something that's greater, second pointer is right there. Now pivot is compared with the other element. If the element is smaller than the pivot one, right, the smaller is swapped with the greater one found earlier. Again, the process is repeated to set the next greater element as a second pointer and swap it with another smaller one. So you've got two pointers. The pivot one stays where it's at. The other one, second pointer, keeps getting moved around. So you swap, move, swap, move. You keep doing this. The process goes on until the second last element is reached. Finally, the pivot is swapped with the second pointer. Okay? And then pivot elements are chosen for the left and the right subarray separately. And then you repeat the step 2 again. The subarrays are divided until each subarray is formed of a single element. And at this point, the array is already sorted. So now you see the trick here, right? In these algorithm, you keep continuing on with the algorithm up until you've reached that one element. And once you've reached the one element case, which is your base case, you've sorted things. That's when you start coming up from the recursion or non-recursion, whichever way you choose. You start combining, right? And this is the pseudocode for. And this is a pseudocode for it. If leftmost is less than rightmost, then pivot index is partition array leftmost and then rightmost. Call quicksort on leftmost, pivot index -1, and then call again on pivot index and then rightmost index. And then this is your partition right here. Okay? Alright, so these are the two, and think of it, which one's going to be slower? Quicksort or merge sort? Some food for thought. The next thing on my list is the dynamic programming. Okay, what's dynamic programming? It's dynamic in nature, okay. Great, but what does it do? Dynamic programming is a technique in computer programming that helps efficiently solve a set of problems that have overlapping subproblems. Now, what all that is um, think of recursion. You have your base case, right? But not all recursive solutions are dynamic. What's going to happen is if you've divided up the problem into multiple subproblems, and if you can work in a way that the subproblem solution will add up to the final solution, then you apply dynamic programming. Otherwise, don't do it, or dynamic programming doesn't apply. Now, one example that I'm going to talk through from here is, yeah, I guess this one I'm going to talk through an example. But it's not a code example, it's an example on the slides itself. Fibonacci series. Okay, let me see if I get my notes here in order because I don't want to confuse you because this could be confusing at times. A Fibonacci series is a sequence of number where each number is a sum of two preceding ones. Okay, so Fibonacci numbers are 0, 1, 1, 2, and 3. 0 and 1. Now, the next number is a combination of 0 plus 1, so you've got 1. And then 1 plus 1 is 2, and then 2 plus 1 is 3, and then 3 plus 2 is 5, right? 5 plus 3 is 8, and then you keep going on and on and on. And now, the base case, what's going to happen is if n is less than or equal to 1, then you return 1. Otherwise, you return the sum of two preceding numbers. So the first term is going to be 0. The second is going to be 1. That's a given, okay? You start off with these two base things in mind. Okay? The third is a sum of step 1 and then step 2. Fourth is a sum of step 3, step 2. Fifth is sum of step 4, step 3. So here you can use cases that you've calculated before. Essentially what you're trying to do is having to do the calculation again and again. Okay, you'll save this work and then come back to it later. So dynamic programming, it works by storing the results of the subproblem so that when their solution are required, they're ready for you. So you've calculated each step, right? So you know F0 is 0, F1 is 1. But when you try to do F2, you're going to take the result from F1 and then add to F0. F3 is going to be the two preceding step. F4 is going to be two preceding step. But in each step, you would have stored the result. The technique of storing the value of subproblem is called memoization, if I pronounced it right. By saving the values in the array, we save time for computation, right? So when you come to this last step, you don't have to repeat the previous step because you stored them already. And then you use the sum of the previous step to get your latest answer. It's a top-down approach. Memoization is a top-down approach by reversing the direction in which the algorithm works. So you start from the base case and then you work towards a solution. Sounds very familiar to recursion, but not all recursive algorithms are dynamic, okay? So keep this in mind. Unless there is a presence of overlapping subproblems like the Fibonacci sequence one that I just showed, a recursion can only reach the solution using a divide and conquer approach. That is the reason why a recursive algorithm like merge sort cannot use dynamic programming, because the subproblems are not overlapping, right? Okay, so now let's talk about the final topic, which is memory management. So C++, it allows you to dynamically allocate memory. You don't have to do it, but it allows you to do it. Whereas in C, you always had to do it. Now that I think of, well, let me go ahead and do memory allocation and deallocation. Let me check something. In Java, memory management. Java. Yeah, in Java it's slightly different because it automatically does the allocation for you and then garbage collection. But C++ is unique in its memory management ways. Um, so I feel you should know this. So this will be slightly off of the topic. Um, No, the book also mentions memory allocation in C++ and then garbage collection. So I'll talk about it. Okay. In other programming languages such as Java and Python, the compiler manages the memory for you. The compiler allocates memory for you, and then in Java you have the garbage collector that comes in at the end and then cleans everything up. But C++ is slightly at a lower level, so you have to do this memory management yourself. You have to allocate and deallocate memory. Now, if you don't allocate it, you have to deallocate it, but it's a good practice to allocate and deallocate. In C, you always had to do it, okay? Well, why do you have to deallocate? Why do you have to release the memory? The simple reason is memory is limited. Now, if you end up using a whole lot of memory, you continue to keep using it without releasing it, you are going to have problems at some point in the end. Um, and the way we go about allocating and deallocating is by two keywords. One keyword is new, one keyword is delete. You can probably guess which one is used for what, right? New is used to allocate memory, delete is to free up the memory. Now, the syntax of new is you take a data type, okay, a pointer variable, and then that equals to the new data type, and in parentheses you give it the value. So below is an example. You've got an int pointer, okay, point var, and then point var is equal to new int. So you're allocating memory for one integer, and then whatever point var is pointing to, that memory that you allocated, in that memory you put 45. Okay, I do have a few examples here. I think I can just jump right into those. This one's got float. Yeah, so let me just talk about delete too, and then at the end we'll. So delete once you no longer need to use a variable that you've declared or for which you've allocated memory, then deallocate the memory for that variable. Okay, and the way you go about doing it is that, like I mentioned, the delete keyword. Okay, delete space the name of the pointer variable. So this is another example. So you've got a point variable and then new int 45, right? Dynamically allocate memory and then assign it to a variable. So if you say cout point var, it's going to output 45, okay? And then at the end you're going to say delete point var. You delete, deallocate the memory and then have it point to a null pointer. Okay. Uh, Having said those, let's jump into some of the examples. So point int integer pointer, I'm pointing it to, I'm allocating memory for one integer, and that integer is 45. Right, there's two different ways. You could have allocated memory in one line and then assign whatever the pointer is pointing to 45. But in this example, I'm doing it all in one shot. And then I have a float pointer, and that's pointing to 45.45, and then I output whatever those two pointers are pointing to. And then I delete both of those, both of those pointers. I shouldn't say delete, but you free up memory for both of those. Okay? Same thing, just using the new keyword. Nothing too complicated here. In this one, now I'm taking a number from the user, okay, and then I've got a float pointer. And then I have a float pointer, and that point, the number of floats is equal to the number that I took in from the user. And then I say enter GPA of the students. And then I go from 1 to that number, 1 to 1, 1 to 10, whatever that number is. And then I say student I plus 1, and then I take in pointer plus 1. Okay? Because you allocated memory for the number of students, and then by doing PTR at I, PTR plus I, you're incrementing it by, what is it, by one memory location every time. So what's going to happen is you are going to end up storing all of those GPAs in the location pointed by that pointer PTR. And then you say displaying GPA of students. And then you start off with I at 0, go to num, and then dereference PTR plus I every time. Okay, and at the end you delete pointer, PTR equal to none. Now what's this? Let's say I have, let's do student 1, 3.1, student 2, 3.2. Okay. And I hope you remember this kind of representation, PTR plus I, right? Now a final example here. So now I'm using a class. Okay, I've got an age in it, and then the constructor initializes the age to 12. Okay, get age equal to 12, and then I get a pointer that's pointing to a new student, right? So I allocate a memory for a new student, and then I do PTR at get age. Okay, see what happens. So essentially what I'm doing is I had a pointer point that to a particular class and then clean up the memory this way. So you can, point being, a pointer can point to any data type, right? Int, float, class, whatever that is. It's up to you. One thing that comes to your mind probably is, well, we were doing fine without it. Why start using it now? Well, flexibility. Dynamic memory allocation allows us to allocate memory as and when needed. If you don't need it, you don't allocate it. Simple as that. And then data structures such as linked lists, trees, graphs, vectors, they often need to allocate memory. Okay? And that memory allocation can vary depending on the size. It's also good for resource management. You've got limited memory. You're going to allocate it very, very carefully. And if it's a dynamic array, which is most likely a vector, you need to resize it. Once again, you'll allocate memory. So, having said that, hopefully that last concept is clear. I will. Well, that's it for this semester. Good luck on your final, and have a good day.